All right, so basically it didn't record my sound for the whole meeting, so I'm going to go through this. We'll go through a little bit slower. I add another slide so we can have a little bit better explanation of latitude and stuff like that, okay? So, all right, datums, WGS84 and NAD83, okay? These are the two most common datums that are out there. NAD83 is used by licensed surveyors in the United States. WGS84 is used by military surveyors, and it's the easiest to transform points from. And then both of those datums, there are map projections so that we can work in horizontal or planar coordinates, right? So if we're doing plane surveys or construction surveys, we don't really want to be calculating latitudes and longitudes. We will just want to work with northings and eastings as if we were surveying on a flat plane to make our calculations and all that kind of stuff easier. Pretty much, we're in the military, we use Universal Transverse Mercator. You might be familiar with the military grid reference system. The military grid reference system is based off of the Universal Transverse Mercator projection, and we're going to get into that a little bit. So number one, here's some just good references if you want to go on these and just research. There's some good information there. Yeah, I know one of them is Wikipedia, but hey, Wikipedia is pretty great, especially if you're trying to learn something new and get some actual references for it, okay? So when we're talking about the datums of 1983 and 1984, the mathematical definition of the ellipsoid or the sphere of the Earth is the exact same, right? So basically it's a squashed sphere. We're going to talk about that on the next slide. But the difference between the NAD83 and WGS84 is the NAD83 was created to transform the Northern American datum of 1927 coordinates because there's a lot of legal definitions for NAD27 as far as property boundaries and all that's concerned. So going from NAD27 to NAD83 is a lot easier than it is going to WGS84, and basically the only difference is the location of the center of the ellipsoid, okay? All right, so when we're talking about ellipsoids, imagine a sphere, right? So with a sphere, you can measure the latitude and longitude of a point on the sphere's surface based off of either what we would be considering the equator and then a meridian, like the prime meridian or the international dateline, right? Now the thing is with the reference ellipsoids, they're a best fit model, okay? So the WGS84 is a best fit model of the Earth's surface for the entire Earth, okay? That means there can be wild fluctuations between the reference ellipsoid and what is actually more representative of the Earth's surface, okay? We're gonna get into that when we're talking about geoid models. Basically, the only difference between the NAD83 and WGS84 ellipsoid is the center point is located 2.2 meters different, and that's because the NAD83 is a best fit model for the North American continent, okay? Now, if you see here, right, so this is a sphere, and then here's a squashed sphere and even a more squashed sphere, okay? So basically, there's a factor here, and it's basically 1 to 300, okay? So basically, for every 300 feet you go out, there's an addition, or sorry, for every 300 feet you go up, there's basically one additional foot that you would go out in the equator, okay? So instead of being just a perfect sphere, it's squashed, and therefore there's kind of a little bit different calculations as far as pulling the latitudes and the longitudes, okay? But it's basically the same, right? So when we're talking about latitude, okay, we're going from, if we're looking at it, right, this is like a side view, okay? So we have our prime meridian. We're going to just call this our prime meridian. It doesn't really matter as far as the meridian is concerned, okay? And then we have our equator, okay? We can also consider this to be the center of the Earth, okay? So the deflection angle from the equator up at a straight line, that would be the measurement of latitude. So this deflection angle here, that's the measurement of latitude. So that would be how far north you are. And then everything is based off of the equator. So your measurements of latitude are either going to be a north degrees minutes seconds or a south degree minutes seconds, okay? Then we have longitude, right? And then it used to be based off of the prime meridian, but it's actually the zones are more based off of the inverse of the prime meridian, which is the international date line. Okay, and basically it's just, hey, here's the prime meridian, measuring in angle that way, right? So you have a deflection angle from there, and that's your measurement of longitude. Okay, so basically what that means is that on a three-dimensional surface, you can use two different coordinates to determine a point. Okay, because it's a surface and it's not doesn't fluctuate. Your horizontal coordinate on here, right? So like this point exactly right here would have a latitude and longitude of that point. That doesn't mean that has a height. It just means that that's the coordinate of the point on the reference ellipsoid. Okay. When we're talking about geoid models, this is more when we're getting into heights. Okay. So with the geoid is the more actual definition of the Earth's surface. We're talking about the definition of the Earth's surface. We're talking more like we're taking what we considered mean sea level, which is the level of the ocean, and using local gravitational effects, we apply that through the continents as far as what would be considered the zero elevation. Okay. Now, as you go through the continents, your plumb line and your local gravitation will change based off of, like a myriad of effects. Okay, so like the elevation can have a difference. Any kind of large deposits of heavy minerals can affect the gravitation in that area. Okay, the geoids are more representative of the actual Earth's surface. Okay, but in order to determine the geoid, we have to have something to reference it to, which is why we have the reference ellipsoid. Okay, so with the reference ellipsoid, it has a smooth arced surface. Okay, the referenced geoid is not smooth. It's not smooth because the gravitational effect in specific areas changes. Okay, for the majority of the United States, the geoid and ellipsoid separation is 30 meters. So the distance between the mathematical definition of the ellipsoid and what we would actually consider to be a zero elevation is a 30-meter difference. Okay, so when you're doing any kind of surveys, you have to understand if you're working with an ellipsoid height, if you're working with a geoid height, because they're two massively different numbers. Okay, and then the orthometric height is basically the difference between both of those. Okay, so your geoid height is going to be fairly basically the difference between your ellipsoid and your geoid at that coordinate point, right? So going back to the tie-in, the latitude and longitude of the ellipsoid in that point has a mathematical separation between the ellipsoid and the geoid. That distance is specified based off of the geoid model. Recently, the National Geodetic Survey has transitioned to the Geoid 18 from the Geoid 12B model, at least for the OPUS observations anybody's getting lately. There is a transformation tool that NGS has in case you want to go back to 12B or go from previous 12B observation to the 18B geoid. I really can't tell you what the massive difference is between those two geoids, but I'm sure that is some differences between them. It just kind of depends on where that information was densified as far as like the gravitational effects. Okay, basically, then what you get is your orthometric height, which is basically the height above the ellipsoid plus the height above the geoid. Okay, and that's what we would consider to be the elevation of the point. All right, either it's an ellipsoid height or it's an orthometric height, which means that there's a geoid added in for the local gravitational effects. Okay, so how the orthometric height works in practice, right? The orthometric height for this point in Fort Leonard Wood is basically 30.672 meters higher than the ellipsoid height is, right? So the height right here, my ellipsoid height, is the distance from my reference ellipsoid, right, to the actual point on the Earth's surface. Okay, not from the geoid to the Earth's surface, from the ellipsoid to the Earth's surface, right? So that's the 313 or whatever. When you add in the geoid definition, that changes it to the orthometric height. Okay, the orthometric height, as you can see right here, is using the North American vertical datum of 1988, using the Geoid 18 model. Okay, and basically this is how you determine what it is, right? So this geoid separation of this latitude to longitude in the Geoid 12b model might be different than the Geoid 18. When I say it might be different, it would be different by maybe a centimeter at most, or 2 centimeters at most. Okay, it just really depends on your area. Okay. This kind of gets into map projections. So with map projections, we're talking about taking the curved Earth surfaces and putting them onto a flat plane. Okay, the universal transverse Mercator projection splits it into 60 zones. Okay, and basically the United States works from basically 10 through 20 ish, right? And each zone, based off of the latitude, has a different convergence factor. So if you see up here, Greenland looks massive, but that's just because the projection makes it so that the shown difference between this point and this point are actually much larger in the projection than they are physically when you're in Greenland. Okay, we're going to talk about that. But each zone is 6 degrees of longitude, right? So these horizontal lines, those are my lines of latitude, and then these vertical lines are my lines of longitude, right? So from here to here is 6 degrees, okay? And each of those is split, that's one individual zone, okay? Now, if you take that individual zone, the meridian, so the middle of the zone, right? Not this line, the middle of the zone, that's where you place this cylindrical shape, okay? When you place that cylindrical shape in the middle of the zone, you create the central meridian, and then you also create these two smaller circles, which is basically, that's how you get the flat plane, okay? When you do it like this, there wouldn't be a convergence factor for changing your latitude, but there will be a convergence factor for changing your longitude, because your lines of longitude converge at the poles, right? So like the distance from here to here is from the same mathematically for the longitude definition, and the same mathematically from here to here for the longitude definition. But the physical distance between those 2 points is not the same. Okay? So here's how this works, right? The UTM convergence is based off of the latitude. Okay, so the meridian right here, they place the zone at 500,000 meters. Okay, and it basically goes from 0 to about 900,000 meters. Okay, so that it allows you to cross over and stay in the same projection if you have to. Okay, so my definition of 1 foot, or we'll say, so this is 0, and then this x of 0, and then this would be x of 500,000. Okay, so my 500,000 from, or actually a better one would be 500,000 is from here, and then to here is 833,967 meters. Okay, and then right here, right, so once we go up to 20 degrees north, my 500,000 meters is still on this meridian, but when I get to my 12 degrees of longitude, my x value is actually 813. So I've lost 20,000 meters between these 2 points. Okay, the further north you go, the worse it gets, right? So this meridian here of 500,000 meters at 60 degrees north, when I go over to the edge of what would be considered the zone, it's actually only 667,000 feet, right? Or 667,000 meters, right? So it's basically the convergence factor is off. The physical distance between these 2 points is different by 200,000 meters. Okay, so the further north you go, the larger your difference in your convergence factor is going to be. Okay, and this is how we're talking about. This is what it really relates to, right? So at this latitude and this longitude, right? Basically my coordinates. I have a northing and easting for my UTM zone. And then I also have my scale factors, okay? All right, with my scale factors, basically this means that at this latitude, 1 meter is 1 meter in the X and Y is actually equal to 0.9996745, okay? So when I calculate the difference between 1 point longitudinally and another point longitudinally, the measured distance might be 1, but the calculated distance between the points of latitude and the points of longitude would be scaled at this factor. Okay. State planes. So each state might have multiple planes. Okay, I'm pretty sure Missouri has 3. The state planes allow for a smaller convergence factor because they've reoriented the projection for their state so that it's easier, basically, so it's easier to survey in that state because it has less of a convergence factor, and that's specifically for planes. Okay.